Today we have a monster integral. So we have this monster expression x to the power x to the power x to the power x to the power x and so on, a tower looking expression, and we have to integrate this from 0 to 1. Obviously we cannot integrate an infinite thing like that, so we first want to convert this to a finite thing. By converting to finite thing, what I mean is, like, if you have root 2 over root 2 to the power root 2, something like this, you know that this equals to 2. So here we have converted an infinite expression to a finite expression. So that's what I mean here as well. So for that, what we can do is we first let this expression as y. If we let this expression as y, we can do a thing. The expression, if you this expression, this infinite expression and the original expression both are same. Yeah, and since the original x to the power x to the power x to the power x is y, so even if we remove the first x and look at only this expression, this will also be y, since both are going to infinity. So we can say y equals to x to the power y. Now, for this we can take log on both sides. Ln of y equals to y times ln of x. Now I need to introduce you to something known as Lambert's W function. Basically, uh, if f of x is x times e to the power x, obviously we cannot take its inverse. Yeah, so what we do, if we cannot do a thing in maths, we just define it. So we define f inverse x to be Lambert W function of x. So this is basically the inverse of this expression. So from the definition, what we have that f inverse of Lambert W function is just x, and Lambert W function, sorry, f inverse is a Lambert W function. So this expression is wrong. I need to write Lambert W function of f of x is x, and f of Lambert W function is also x from the definition. And you might wonder what's the benefit of just defining an inverse. Yeah, there are some benefits, because we can of course have an infinite series expression for this f inverse x, and now we can assign that infinite series to Lambert W function, and from then, if we are not able to take the inverse, we will just define it as Lambert W, and now for Lambert W of 2, Lambert W of 3, or anything like that, we can just use the series to find the value. So this will make sense after we have series expansion, and we do have that. So that's how it's useful. And okay, so this expression will evaluate to, since f of x is x e to the power x, so Lambert W of x e to the power Lambert W of x, so this is also x. So about Lambert W of x, I want you to know some of these properties, these four properties, I guess, because we are going to use these properties later on. So now I have just introduced Lambert W in the middle of the solution, but here now we will have some of the uses of Lambert W now. Here now, how do we isolate y? Obviously, there is no definite way to do that if we just look at generally, but we can do something like this. First, we can take this y to other side. Yeah, no, just please catch up what I'm doing. So we can first take it to other side. Now we can just introduce a negative sign, and then also we can have the power of y as inverse. So this negative sign basically comes out of the logarithm and cancels with this one. So you can do that. Now we can just raise this y inverse to the e ln power. So e to the power ln of y inverse. You can do this since e and ln cancel each other. Now we can see something similar. Yeah. Now what we basically had, f of x, if f of x is x e to the power x, then f inverse x was Lambert W function. Whoa. So if f inverse x was Lambert W function, so then this f of x should be Lambert inverse x. Yeah. So Lambert inverse x is basically x e to the power x. Okay. You should get that. Now this expression is just Lambert inverse of ln of y inverse, isn't it? Yeah. So that makes us easier to combine this y into a single expression, and that's how it's useful. Now we will just take negative sign to the other side. Lambert inverse of ln of y inverse is negative ln x, and then ln of y inverse is Lambert of negative ln x, and then y inverse is equals to e to the power Lambert of negative ln x, and then y equals to 1 over e to the power Lambert W function of negative ln x. Sorry, negative ln x. Now to further simplify this expression, we will use the property that I already mentioned, that f of Lambert W function is just x. So f of x was x to the power x, so this will be w Lambert W of x e to the power Lambert W of x is just x. So we get that Lambert W of x over x will be 1 by e to the power Lambert W of x. So now using that, we can have it as y equals to Lambert W of here, what is it, the same thing, and negative of same thing. Yeah. So we use this formula, and now we have this infinite expression y in terms of a finite expression, which goes like this. So now we will try taking the integral now. So we have integral from, what are the limits? I forgot it. From 0 to 1. So integral from 0 to 1, and the infinite tower is basically what we have here, Lambert W of negative ln x over negative ln x dx. Now we can basically use the series expansion for Lambert W function to proceed to the integral, and the series expansion of Lambert W function will be quite helpful for us now to further evaluate this expression. And the series expansion goes like this: Lambert to ln x. Series expansion of Lambert W function is sum from n equals to 1 to infinity, and negative 1 to the power n minus 1. I don't know why it's happening. And then n to the power n minus 2, and we have over here z to the power n over gamma of n. So this might look monstrous, but it will not be during the simplification of here. So we have integral from 0 to 1, and then the series expansion is sum from n equals to 1 to infinity, and negative 1 to the power n minus 1, n to the power n by 2, and our z is negative ln of x to the power n by gamma of n. So this was the Lambert of negative ln x. We have over here negative ln x and dx. Now since this negative ln x is a constant for the sum which involves the variable n, So since the sum is in the n world, ln x will be just constant, and we can bring that inside summation notation. Sorry, summation n is greater than or equals to 1, and negative 1. Since we have negative 1 to the power n over here, and if we add it here, it will be 2n minus 1, and that's just an odd number, so negative 1 to the power odd is just negative 1. So you can make it like this, and n to the power n by 2, ln x to the power n by negative ln x gamma of n dx. Now we can interchange the summation and the integral, and so this comes out to be summation from n greater than or equals to 1, and since now if we are integrating, that will be in the world of x, so these n terms will be constant, which you can take out, and again this negative 1 and negative 1 over here will cancel, so no need to write that, and n to the power n by 2 by gamma of n, and integral from 0 to 1 ln x to the power n minus 1 dx. Now we will easily evaluate this integral using some beta gamma function, but for that first we need to have y equals to ln x as substitution, which will give us e to the power y as dx. We will just first evaluate this integral, and then we will come back to it later on. Alright, let's do that. Now this integral will be 0 to 1, and sorry, we need to change the limits. So when it's 0, it's negative infinity, and when it's 1, it's 0, and it's y to the power n minus 1, and our dx will be just e to the power y dy. So e to the power here I have just missed. Okay, after this we will have e to the power y equals to x, and then e to the power y dy equals to dx. Yeah, that's fine now. And then dx is just e to the power y dy, and now we will change y into negative y, so that will lead us to since we will have negative dy, we can just reflect the limits of integral, after negating those limits, and then we will have over here negative 1 to the power n minus 1, and y to the power n minus 1, e to the power minus y dy. So now this one is of course a well-known thing for us. It's just the gamma function for n. So it's just gamma of n over here, and that was quite familiar for us. Now we can place it back in the integral, this integrals. So now we have this sum from n is greater than or equals to 1, and this is n to the power 2 by gamma of n, and this integral is just negative 1 to the power n minus 1 gamma of n. Now the gamma of n just cancels out, and we have summation n is greater than or equals to 1, n to the power n by 2. It's not actually n by 2, it's n minus 2. I just messed it up, but let me just reconsider this. So n minus 2. So just consider that we are being n minus 2. Forgive me for that. So it's n to the power n minus 2 and minus 1 to the power n minus 1. Okay. So now if we just try to look at how this sum looks like. So when we have n as 1, this will be minus 1 to the power 0, so that's 1, and here we will have 1 to the power minus 1, and next term will be for 2 is 2 to the power 0, so that's negative 1, and then we will have 3 to the power 1 and negative 4 square plus positive 5 cube minus negative 6 to the power 4 and so on. Now we can see that from the nth term test, the nth term is of course not 0, so it fails the divergent. So it fails the from the divergent test we can say that this sum actually diverges. Yeah, since nth sum is not 0, so it fails and this series diverges. And now we know that the integral actually diverges. So our this integral actually diverges. But did we need to do all this integral to know if it diverges or not? Actually, we could have found out this thing in the middle too. Yeah, we needn't go up to the end of the integral. So over here when we got that y equals to lambda of negative ln x by negative ln x. So here the for any lambda of x, for the lambda of x series to actually converge, the modulus of x should be less than 1. For lambda of x series to converge, the modulus of x should be less than 1. If we had used this fact, we would have found out it earlier as well. So now let's see what happens when we know that fact. So we got that for x to the power x to the power x to the power x being y, y is also equals to lambda of negative ln x by negative ln x. So now the series of lambda of x converges only when modulus of x is less than 1. So over here, modulus of negative ln x should be less than 1. So modulus of ln x should be less than 1, and that implies negative 1 is less than ln x is less than 1. And we can just exponentiate in all the terms. That gives us E inverse is less than x is less than E. So for actually this series to converge, we need to have x in between E inverse and E. Only then this series will actually converge. Okay, and the root 2 is also in the middle, so that's why we got the root 2 to the power 2 to the power root 2 to be 2, else we would not have got. Now for this series, since we have the x values from 0 to 1 and E inverse is actually greater than 1 for none of the values over here, or is it? I guess it isn't. No, it isn't. Of course 2.7 is of course less than 1. Okay, so anyway, even though for some of the values in the integral, this x to the power x to the power x to the power x, it converges, but for not all values. So let me check what is 1 by e. 1 by e is actually 0.36. So 1 by e is actually 0.36. So for the values that are lesser than 0.36, when x goes from 0 to 0.36, the term actually diverges. So that's why the integral also had to diverge. Though from 0.36 to 1, if we take this integral from 1 by e to 1 to e, let's say, this integral might converge. Of course it will converge, it can converge, but this one over here will diverge, because in some of the terms that integral is running, this x to the power x actually diverges. So that was the reason the integral also did diverge, and we could have known it in the middle as well if we here check that this input of Lambert's should have modulus less than 1. Okay, so that would have given us x should lie in between E inverse to E. So that was the takeaway from this video. So I hope you knew a lot about Lambert double function from this. And thanks to Maths 505 for coming up with such similar problem and letting me just dive deep into it. So thanks for watching. I'll see you in the next video. Hope you enjoyed it.